second speaker for today is Liat Kessler, who is going to talk about from symplectic deformation to isotopy equivariantly. Please, Liat.
Thank you. Thank you, Sylvia. And of course, I'd like to thank the organizers for inviting me. I'm very happy to be part of this celebration for the wonderful people and great mathematicians. Yes, I will talk. I will explain. I think the title will be understood by the end of the talk. And this is a joint work with Pranav Chakravarty, River Chang, and Martin Pinsonol. They are all here. So if you don't understand something, you can ask them. What we want to understand is we want to understand whether the space of equivariant symplectic ball embeddings is path connected. We look at group actions. In particular, in this talk, I'll talk about a circle action on a compact symplectic four manifold. And we look at the space of embeddings of balls, and we fix these are balls. These are, when I write B4R, I mean a closed ball whose center is the origin and the radius R, and we fix R. We also fix a connected component of the fixed point set. So we look at the space of symplectic ball embeddings from the ball of radius of the given radius R with the standard symplectic form that are centered at the point of this fixed connected component of the fixed point set, and we ask whether this space is path connected. So the ball, right? The ball, we have chosen what is the symplectic structure we take on the ball. That's the standard symplectic structure, and the circle action on the ball will just be the linearized action of the circle. So the circle will act through rotations on the ball according to the isotopy weights at the fixed component. Okay, so this question translates naturally to a question about the uniqueness of the equivariant symplectic blow-up. So what does it mean that we have an embedding of a closed ball? It means that we have an embedding of a slightly bigger open ball, and in that slightly bigger open ball, we can perform an equivariant blow-up, equivariant symplectic blow-up of size R. Right? So as usual, we take out a ball of size R and we collapse the boundary along the Hopf vibration. And this, right? If this, right, the circle action, and in general, if you have a G action, it will descend to the blow-up. Right? So once we have an embedding, it automatically gives us a blow-up, and if the embedding is equivariant, it will give us an equivariant symplectic blow-up. So now we ask, is the equivariant symplectic blow-up of the manifold with the action of a given size at a given connected component, is it unique? And for us, unique is up to equivariant isotopy. So let me just recall what we mean by isotopy. We say that two symplectic forms are isotopic if there is a deformation between them. Deformation means that we just have a path of symplectic forms between them. And so that just means that they are deformation equivalent. And isotopic means that the cohomology class of all the forms along the path, including at the endpoints, is the same. So that's an isotopy. And by Moser, if you have an isotopy, then you also have a strong isotopy, meaning that you have a diffeomorphism connected to the identity that pulls back omega 0 to omega 1. And of course, we can do all that in the equivariant setting. So we can talk about invariant symplectic forms, and we can require that all the forms in the isotopy will be invariant symplectic forms. And so then that will be what we call an equivariant isotopy. And again, an equivariant isotopy will imply a strong equivariant isotopy. So this question was answered in the non-equivariant setting. It was answered by McDuff in 96. So now we look at, we restrict the manifold that we consider. We look at manifolds that are either the projective plane or a ruled symplectic or ruled symplectic 4 manifold, or a blow-up of such a manifold. A ruled symplectic 4 manifold is just an S2 bundle over a Riemann surface with a symplectic form that is symplectic on each fiber. And McDuff showed that if you look at such a manifold and you fix the size of the blow-up, then there is a unique way to blow up a point in the manifold to that size, again, unique up to isotopy. And when you correspond isotopy classes of symplectic forms and isotopy classes of ball embeddings, this translates to a result on the space of embeddings. So this says that the space of symplectic ball embedding of a given radius into our manifold is path connected. So that's in the non-equivariant setting, right? Here we don't have a G action. Let's go over a McDuff proof. So we start with 2 embeddings of a ball of the same radius. And first we find a path between them. So the way we find the path is we shrink both embeddings from both sizes, right? So we just shrink the size of the ball. And then we get to a size, to an embedding of a ball that is small enough, and there it is known that every 2 embeddings of this size will be isotopic. The size might depend on the embeddings, but still, if we get to a small enough size, we will find an isotopy between the embeddings. Okay. And so now when we perform a blow-up along the embeddings, right? So each embedding we said will give us a blow-up. We perform the blow-up in the standard ball, and then it will transform through the embedding to a blow-up of the manifold. So now we get a path between the blow-ups that we got from, right? Omega 0 is the blow-up form that we got from the embedding I0, and omega 1 is the blow-up form that we got from I1. And we will get a path of blow-up forms between them, but it will not be an isotopy, right? Because here we have an isotopy, but here the sizes of the blow-ups are different, so the cohomology class of the form is different. So to fix that, we have to somehow find a path between each form in the deformation to a path, to a form in the cohomology class of our omega 0 or omega 1. And we have to do that simultaneously, right? So for that we use the inflation process. And again, I will give the statement soon, but the way we think about inflation is it's some process that will give us a path between a form here, right, or here, so a form along the deformation to a form in the same cohomology as omega 0 and omega 1. And moreover, we can do that simultaneously, so you can inflate a path into a path between omega 0 and omega 1, and that's the required isotopy. And of course, once you have this isotopy, it's actually isotopy of blob. All the paths along the way will be blob forms. You can blow down and get an isotopy, get a path between the embeddings. Okay, so blow up takes you from embeddings to forms, and blow down from forms to isotopies, to embeddings. Okay, so I do want to state the inflation lemma, and for that we have to recall the notions of an almost complex structure and a geolomorphic curve. So an almost complex structure is just an automorphism of the tangent bundle that's square to minus the identity. And we say that it is tamed by omega if for every non-zero vector, if you plug in v and jv, you get a positive number. And we say that it's compatible if, in addition of being tame, it's invariant to j. So omega jv jw equals omega vw for all vw. So an almost, of course, that every complex structure induces an almost complex structure, right? Every complex chart induces an almost complex structure, using the multiplication by I, but not necessarily every almost complex structure comes from a complex structure on the manifold. This is an observation of Gromov. You can still you can still talk about holomorphic curves even in the setting of almost complex structure, and it will still carry information on the manifold. So what is a holomorphic curve is just a map from a Riemann surface to our manifold that satisfies the Cauchy-Riemann equation, right? So J composed on dF equals dF composed on J. The small j is the complex structure on the Riemann surface. And of course, if J is omega tame, then if you have an embedded holomorphic curve, it will be an embedded submanifold of dimension 2. Yeah, an embedded symplectic submanifold of dimension 2. So now we can state the inflation lemma. So this lemma, of course, has a history. It started with Lalonde, then developed by Lalonde and McDuff. At that stage, like Martin explained to me, they understood that you can inflate along the class of geomorphic curves, but they didn't care whether the forms you get are tamed or not tamed by the complex structure you started from. And also both Lalonde and McDuff and McDuff in 2001, they only cared about the case, or they only, I don't know if they only cared, but they only stated the inflation lemma for curves of homology class whose self-intersection is non-negative. Then Booth, later, she also stated the inflation lemma for and proved for classes of negative self-intersection. So that gives that was very powerful. But all of them had a small mistake that imposed an unnecessary bound on the size of the inflation. And recently, Chakravarti, Payet, and Pinsonol have solved that, both for the two different solutions for so one for the non-negative case and one for the negative case. So you can find that in the archive. So the statement I'm giving here is the statement of Chakravarti, Payet, and Pinsonol. So you start from an embedded two submanifold that is geomorphic with respect to some almost complex structure that is tamed by omega. And the inflation lemma guarantees that we can find a family starting at omega of symplectic forms, all tame in J, in the cohomology class of omega plus some multiple of the Poincaré dual of the homology class, the Poincare of the homology class of our submanifold Z. Depending on the self-intersection of Z, we have a bound on how much we can inflate. So if the self-intersection is non-negative, this bound is infinity, so we don't really have a bound. If the self-intersection is negative, then the bound is the size of Z over minus the self-intersection. So for example, if Z is of self-intersection -1, the bound is the size of Z. And this can be done, so this can be done for a path of such forms and J's and Z's. So this can be done simultaneously for a path. And so when McDuff applied the inflation lemma, so you see, to apply the inflation lemma, you have to find these Z's, right? You have to find geomorphic curves for omega tame J, and you have to find them in the correct classes, right? The correct classes meaning such that when you find this path, eventually you will get to the cohomology class that you want to get, right? To the cohomology class of omega 0 or omega 1. The way you usually do that is that you inflate and then you divide by some size, and then you get to the correct class. So McDuff needed to find enough geomorphic spheres or geomorphic spheres in specified classes, and she had to find it for some omega tame almost complex structure. So she found it for a generic omega tame almost complex structure using the theory of Taubes, of the equality of the Zeiberg, Witten, and Gromov in this case, right, of a complex symplectic form manifold. So that was this is a key part in the proof of McDuff in the non-equivariant setting. So we will talk in a second of what survived the moving to the equivariant setting and what didn't. So our goal is to give an equivariant version of McDuff result. So to show that the uniqueness of an equivariant symplectic blow-up up to equivariant isotopy, or to show the path connectedness of the space of equivariant symplectic ball embedding once you set the size and the fixed component. I will talk today about, so most of our work is for Hamiltonian S1 actions. Maybe I'll say a few words. We are interested also in the case of finite cyclic groups. So first of all, like we ask ourselves, does it follow from other results? As you'll see, our proof will not be that trivial. So if someone has already done it, we shouldn't work so hard. So the first attempt is to see if you can just get, so these two invariant forms, they're in particular symplectic forms, symplectic blow forms. So McDuff's theorem will give a path of symplectic forms between them. So maybe you can just average them, right, with respect to this compact action. Maybe you can just average them and get a path of invariant symplectic forms. So you can average them, but you will not necessarily get symplectic forms again.
Is this because the J was not invariant?
Exactly.
If it were, then
It's what?
if the J was invariant?
If the J was invariant, but the Zeiberg-Witten equals Gromov only gives you a generic, or only tells you that for a generic almost complex structure, it will be a generic almost complex structure will be omega tame, and in that structure you will find the required spheres or curves, but not necessarily for an invariant almost complex structure. So that's a key. So when you average, you don't necessarily get non-degenerate symplectic forms. So of course, if you had an invariant almost complex structure, such that all forms were attained by it, then the averaged form would still be non-degenerate, right? It will still be attained. So but the Gromov-Witten invariants don't give us, right? And they give us many almost complex structure, but not necessarily an invariant one. So that's a key point. So we cannot just apply, just average the path that we get from McDuff. And then the other question is, didn't Yael already prove that? So let me just recall what Yael did. So Yael classified compact connected symplectic form manifolds with Hamiltonian S1 actions, and she classified them by the decorated graphs associated to them. Let's just recall what it means. So for every isolated fixed point, there correspond a thin vertex, and for every fixed surface, there corresponds a fat vertex. And all the vertices are labeled by their moment map image, and they are also placed according to their moment map image, right? So you think about their moment map value. So you think about the moment map value as height. The fixed surface are also labeled by their symplectic area and their genus. And you also have a label for spheres, right? So if you have two fixed points, there will be a sphere, a gradient sphere between them, and so there will be. So you have labels for spheres on which the circle acts by rotation of a speed greater than 1. Right, so these are the ZK spheres. So you also have labels for ZK spheres. Questions? Okay. And Yael showed that the decorated graph determines the Hamiltonian S manifold up to equivalent symplectomorphism. So if we have two manifolds of the same decorated graph, there will be an equivalent symplectomorphism between them. In particular, if we start from a Hamiltonian circle action on a manifold, and we perform two equivalent blow-up at the same fixed component by the same size, then the decorated graphs will be the same. So Yael's theorem will tell us that there will be an equivalent symplectomorphism between the manifolds. But equivalent symplectomorphism is not enough for us. We want an equivariant isotopy. And of course, the equivalent symplectomorphism that you have between the two manifolds is not necessarily isotopic to the identity. Right? There is no reason that it will, right? So the fact that they have the same decorated graph told us that they are equivalently symplectomorphic, but not necessarily equivalently isotopic. So another thing that we get from Yael, which was nice, Yael also described all the possible symplectic manifolds that admit S1 actions. So they are just blow-ups of the projective planes or ruled form manifolds. So it's okay for us to only investigate blow-ups on such manifolds. And the only other result we know in the equivalent setting is the result of Pelayo. And Pelayo showed that if the action is toric, then the blow-up is indeed unique up to equivalent isotopy, and the space of embedding of ball embeddings, of a given size centered at a fixed point, at a given fixed point, is path connected. Pelayo's proof is different. It doesn't use holomorphic curves. It's more combinatorial. And the key ingredient in Pelayo's proof is that in the toric case, the pre-image of a point under the moment map is an orbit. Of course, that for Hamiltonian S1 actions, this is not true, right? The dimensions are not correct. The pre-image of a generic point will be of a dimension greater than 1, and usually a union of orbits. So even for the standard action on C2, right, the pre-image of a point that is not 0 is a 3-sphere, and it's a union of circles. Okay, so we have to work, and no one else has done, right? And we cannot use Pelayo's work, and what we do is not what is proven by the uniqueness, right? By the uniqueness up to equivariant symplectomorphism, and we cannot just average the path we get from McDuff. So we want to redo McDuff's work, but in the equivariant setting. Right, so remember, she first gets a deformation by shrinking the size of the ball and finding an isotopy for a ball small enough. And then she uses inflation to get the isotopy. So we need to find this deformation equivariantly. And if we want to use inflation, we need an equivariant inflation lemma. So this is quite, so to do the deformation equivariantly is quite standard. It requires arguments, but it's doable. And the equivariant inflation lemma, that was proven by Pranav, Martin, and Jordan in the same paper that they've just recently submitted. And so we also have the equivariant inflation lemma. What we don't have is the fact that we have non-zero Gromov invariance in these classes that McDuff uses doesn't help us anymore, right? Because like we said, they will give us geomorphic curves, but not necessarily with respect to an invariant almost complex structure. And we need, right, if we want to perform an equivariant inflation, of course, we have to add invariant everywhere, right? So the holomorphic curves we use have to be with respect to an invariant almost complex structure. So we cannot use the result of Taubes, and instead of that, we have to find the curves that we need to actually say these are the curves. That's how, and we know that we have geomorphic curves in these classes, and these are the classes that we are using. So we will not inflate along the classes that McDuff used. In these classes, we don't necessarily know that we have geomorphic curves with respect to invariant almost complex structure. We will inflate along other classes, so we have to give a different algorithm for how to use inflation. And we also have to prove that in these other classes, we do have geomorphic curves with respect to an invariant almost complex structure at least for Hamiltonian S1 actions. So the way we will find the curves that we look for is by looking at the decorated graph. So I will start with an easy example. In that example, we don't even need the decorated graph. So, so we have mu that is greater or equal than 1, and c that is smaller than 1, and gamma that is still positive but smaller than c. And we start from some Hamiltonian S1 action on S2 cross S2 with the product form, right? So, right, with the parameters mu and 1, and some fixed component sigma. And we look at two blobs at the same, again, both performed at sigma, but one of size c and one of size gamma. And we want to show that there is a family of right? There is a path of invariant symplectic forms connecting omega prime, so the one that was blown up by the smaller size, and omega, right? The one that was the blow up by the bigger size, right? So this, right? So this is what we need in this stage, right, of McDuff's algorithm, right? So we said we can get to the deformation, we can get an equivariant deformation. That's okay, and right. But now we need to go right to use inflation to go from each form in the deformation to a form in the cohomology class of omega 0 and omega 1, and right. So what we claim is that we can do this part right in the equivariant setting, right? So I'm only talking about this red orange part here. Okay. Okay. So in this example, we know that thanks to Yael that all Hamiltonian S1 actions actually extend to a toric action. And so if you look at the decorated graph, they are all projections along some rational slope of Delzant polytopes. Right, so the moment the right and from Delzant, the possible Delzant polytopes, right, will be obtained, right, that they will be obtained from a trapezoid, an Hirzebruch trapezoid, right, of slope R or 1 over R, right, where R is a positive, where R is a non-negative number that is strictly smaller than mu, right? Then you remember what was mu, okay? Right, so we start from a trapezoid, the letters here represent the homology class of the pre-image of the edge of the trapezoid, okay? So we start with some trapezoid whose edge, right, correspond to spheres in the indicated homology class, and we perform a toric blow-up, right? So in the picture, what we get is a corner chopping at some corner. And we have two possible ways to perform the blow-up, right? We can either perform them at the long edge or at the corner that touches the long edge, or at the corner that touches the short edge, right? So these are the two possible types of toric actions on this blow-up of S2 cross S2 with the form mu tau plus tau, and of course the R may vary. But right, so again, we know that each of the pre-image of each of the edges, right? So these are right. So we get polytopes. So we get again toric actions, and we know that the pre-image of each of the edges is an invariant sphere in the indicated classes, right? So we also have, now we have one in E and one in F minus E. And if the blow-up was at the short edge, then we will have a sphere at B minus RF minus E. And if it was on the long edge, then it will be at B plus RF minus E. So the pre-images of the edges now will be J-holomorphic spheres for some invariant, even integrable complex structure. J, and it will be invariant with respect to the torus action, but in particular, it will be invariant for the circle action, right? The circle is now, we think about it as a subcircle of the torus. And
So you had two different symplectic forms, both S1
right, but I got both of them by by an S1 invariant blowup of different sizes, but at the same point or at the same fixed
Can
component.
you find a toric action that is compatible with both of them? Like your toric, the extension of the action.
Yes. Yes, and actually they are not random, right? What I'm looking at is one will be obtained from the other by shrinking the size of the ball.
So you use that to
Right.
construct the toric action,
Yes.
which is in
Yes.
some sense compatible with both of them.
Exactly.
So then it's the same J for both.
It's the same J for both of them. Yes, that's a key. Because if it's the same J for both of them, then there is the same configuration of holomorphic spheres for both of them.
Actual same spheres.
Actual same spheres, yes. They will have different sizes with respect to the different symplectic forms, but they will be the same spheres. So right, and this configuration of geomorphic spheres, right, in the first case, right, we will have spheres in B plus RF and F minus E and B minus RF minus E minus F, and B minus RF minus E and F. And in the right case, right, we will have geomorphic spheres in F minus E, B plus RF minus E, F, and B minus RF, and again, for both symplectic forms. Of course, that here, right in the right side, we can assume that R is positive because otherwise we would have been in the left side. And I just reminded here what is B and F. So, right, B and F are the classes of S2 cross a point and a point cross S2, and E is the class of the exceptional device. Okay, so again, we have form that was obtained from from our form by shrinking the size of the ball, and now we want to inflate it such that it will be in the same cohomology class of the original one. So we have to inflate, right? We have to inflate along a class of the form A minus E, right? Why do I need the minus E? Right, because remember the inflation will give us a path to a class in the homology class of this omega prime plus right, something times the Poincare dual of our, right, of my form, of my class. So, right, so if I inflate along a class in A minus E, so the size of E now, right, will be the size it was, will be the size by omega prime plus some size time the Poincare dual of A minus E. So E dot A minus E will be, E dot A will be 0, and right, so we need that for A such that, I will say in a second, but all I need from A is that its intersection with E will be 0. Right, so if I take A such that its intersection with E is 0.
So A came from?
A will be one of these, B plus RF or F.
The one from before the.
Right, A came from before the blow up. Right, so if I look, right, so now I have, right, so now I have a path to a form in the class of omega prime plus a lambda times the Poincare dual of A minus E, right? So if I'm looking at what is the size of the new, or what is the size of E under this form, so it will be the size that it was under omega prime, right, which is gamma, and plus lambda times the intersection of E and A minus E. But the intersection of E and A minus E is plus 1. Right, that's why I need the minus E.
This is a class whose Poincare dual
So I do the inflation along this class, and then I evaluate it at E, and this will allow me to increase E. Right, so to decrease E, it's very easy. I will just inflate along E itself, right? Because it's the intersection of E and E is -1. But if you inflate along A minus E, because the intersection of A and A minus E is +1, then when you inflate along it, you increase the size by lambda. So inflating along A minus E allows me to increase the size by lambda. But the problem is that once I inflated along A, or along A minus E, then I change the sizes of other classes. For example, if A is F, then the size of B will increase, right? Because the intersection of B and F is 1. And if A was B, then the size of F will increase. So I will have to do further inflations so that I will readjust the sizes, and then eventually I will divide by something that will send F back to 1 and B back to mu, and E will still take to C. Right, so I have, right, so again, then the main thing is to give an algorithm that will tell what are the correct classes to inflate along, and that you can actually do that. You can inflate along the classes. And recall that to inflate along a class of non-negative positive intersection, right, you don't have any restriction on doing that. But to inflate along a class of negative self-intersection, for example, F minus E, then right, you can only inflate by a size that is smaller than the size of that class. So this is very sensitive to the order in which you perform the inflation. So you first, right, if you want to inflate along the F minus E, you will first have to inflate along something that will increase F, and then will increase also F minus E, and then you have freedom to inflate as much as you need along F minus E. So we have to, I mean, it's not trivial to devise the order and the classes that you need to use. In this case, it was easy to show that you have indeed geolomorphic curves in these classes. So for example, in the left case, we inflate omega prime first along B plus RF, and then along F minus E. The reason we do that in that order, again, is that inflating along B plus RF will increase both F and B, and so it will also increase F minus E, and we can inflate it by the size we would like. In the right case, we first inflate along B plus RF minus E. Because we assume that R is positive in that case, then this will have a non-negative self-intersection, so we have no limit on the size of the inflation. And then we inflate along F, and of course we have to say what are the sizes. The sizes will depend on which case we have, the left or the right, mu, C, gamma, and of course R, right, in the configuration. Okay, so that was in the special case that right of blow up of this action, and in that case we didn't even need the decorated graph because we already could use the polytopes, the Delzad polytopes, and get geomorphic spheres as pre-images of the edges. Right, so geomorphic spheres with respect to some invariant structure that is compatible and in particular attained with both. Of course, that not always we have a toric action, right? For example, this action does not extend to a toric action. Once you have these 3 points of the same height tell us that. And also, we can't always, right, so for example, in the previous example, we saw that we wanted to inflate along classes like B plus RF or B plus RF minus E, F minus E, F. We will not always have geomorphic spheres, right, or spheres that correspond to edges or fat vertices in the decorated graph in these classes. So sometimes we will have to inflate along cusp curves, not along curves. So sometimes we will have to inflate along chains of geomorphic spheres, maybe even with coefficients, right? So for example, this is an S1 action, and that is obtained by, right, you start from an S1 ruled symplectic form manifold, right? So you start with an action on S2 cross S2 with two fixed spheres, and you perform 3 blobs, right? One from the bottom, one from the top, and another one on an isolated vertex you got in the second blob. Is that okay? How you got this? Is that okay? Oh. So that's a decorated graph. It's actually an extended decorated graph because there are also edges for free gradient spheres, right? Edges on which the circle act by speed 1. So that's a decorated graph of some circle action on right on S2 cross S2 blown up 3 times, and we see that here, right, we still have a geomorphic sphere in the class E3, right? Because we have so once we have an extended graph, every edge in the graph and every fat vertex correspond to a geomorphic sphere with respect to some invariant almost complex structure. This is how the extended graph is constructed. And so in this example, right, we have this edge of label 2. This will correspond to a holomorphic sphere in E3. And we have the fat vertices. They will correspond to holomorphic spheres in B minus E1 and B minus E2. And the other edges, right, they will also correspond to holomorphic spheres in these classes, right? So we have holomorphic spheres in B minus E1, F minus E2 minus E3, E3, E2 minus E3, B minus E2, F minus E1 and E1. Right? The edges of the extended graphs correspond to geomorphic spheres for some invariant, not necessarily integrable, almost complex structure. And if we tried to do the algorithm we did in the previous example, then we see that we don't have geomorphic spheres in the classes that we need, right? We don't have a geomorphic sphere in F minus E2, and we don't have a geomorphic sphere in B, right? Or in B minus E3. So we will need to use chains of holomorphic spheres that you got out of edges and fixed surfaces. For example, E2, right, will be represented by a chain of a sphere in E2 minus E3, right, the top one there, and E3. And F, right, there are several ways to see F. But in one of them, it's a chain of spheres in F minus ET minus E3, E2 minus E3 plus a sphere in E2 minus E3 plus 2 in E3, right? So that's what I said, that there will be cusp curves, maybe with coefficients, right? Not necessarily all coefficients are 1. So maybe with coefficients that are bigger than 1, still integer coefficients. And F minus E1 will be represented by the same chain of spheres, right? But with a different coefficient. E3 will be with coefficient 1, not with coefficient 2. And B will again be represented by a chain of a fixed surface and an edge, right? So we will have to inflate along these classes, and it means that we will have to inflate not just along geomorphic curves, but along chains of geomorphic curves, again, maybe with coefficients, because that's what our algorithm knows to do. We need spheres or geomorphic spheres in this, or spheres or cusp curves in these classes. So for that, we need to know how to inflate not just along spheres or curves, but along chains of curves. And what we do is we were inspired by Booth and Lee. So Booth and Lee showed us how to inflate along the cusp curve in the special case that the cusp curve is in a class of self-intersection -1, and you have exactly two components, one in a class of self-intersection -1, one in a class of self-intersection -2. The intersection between the two classes is 1. And they are both represented by holomorphic spheres with respect to, in their case, to some compatible, almost complex structure. And in that case, they showed that you can find a J-tamed symplectic form in omega plus lambda times the Poincare dual of E, where lambda is bounded by the size of the component of self-intersection -2. And
Sorry, saying, are you assuming that E equals E1 plus E2?
Yes, right. So E is represented by a cusp curve whose components are in D1 and D2, right? So E equals D1 plus D2. And what it means is that it's like, okay. Okay, so 1 minute? Yeah. Okay. What it means is that you can reduce the size of E almost by the size of this D2, right? Because, if you like you said, if you look at the size of E under the new form, it will be what it used to be minus, right? Because E dot E is -1 minus lambda. So at most minus the size of D2. And what we do is we generalize the result, and we do it for many more cusp curves, enough so that we can prove, we can redo McDuff's argument in the equivariant setting. Thank you.